Okay. Sige. So, our lessons for today is about electrostatics, no? So this is a very cool term, and PN junctions. So PN junctions are something that you guys all love probably because this is this thing, no? So if you don't remember what this thing is, maybe you need to go back to your previous lessons. But these two are what we're going to be talking about today, no? So what is electrostatics? Electrostatics is what electric things do when we don't do anything with them, no? For example, a semiconductor in equilibrium, no? So, semiconductors in equilibrium. So when a semiconductor is in equilibrium, no, we already actually know this, right? Because for a semiconductor in equilibrium, the Fermi level, actually, the fact is the Fermi level EF is constant. Space, no? Space, which is X in most of the examples that we've been through, no? So an example of this is probably the original energy band diagram, no? So let me draw an energy band diagram here. I'll place EV. Whoops, everyone knows that's wrong. No, that's the edge of the conduction band because it's above, no? And this one would be the valence band edge, no? This would be EI. Now, if I were to dope this semiconductor with donors, which increase the number of electrons, right? If we increase the number of electrons, then the new Fermi level would be around here, right? Bakit natin alam yon? Because of EF, because of KTLN N over Ni, no? This thing is the difference between EF and EI, no? On the upside, no? On the positive side. So that's how we know na pataas si EF if the semiconductor is N-type when there's more electrons than there are holes, no? And observe that if these were all functions of X, no? And this was the X direction, then this means that the semiconductor is in equilibrium. Intuitively, we could say na this happens when nothing is happening on the semiconductor, no? We leave it on the table and observe it, no? That means no current should be getting out of the semiconductor, and so no net current should be escaping out of the semiconductor, no? Now, the thing is, take this case, for example, no? So we have the spatial dimension X, no? We have the spatial dimension X, and I were to vary, no, the doping with respect to the dimension X, no? So let's say this is the donor doping concentration, no? And say this is around 10 to the 17, tapos dito mga 10 to the 13 na lang siya, no? So I varied the doping concentration, no? What would happen actually is yung Fermi level natin, it would strive to remain constant, no? Over the semiconductor. So what happens is, let's pull that up there. So what happens is, dun sa semiconductor natin, no? Dun sa semiconductor natin, since the position, no, of EF minus the EI, no, should be KTLN over Ni, no, which we could probably approximate as ND over Ni for both of these cases, no? Bakit? Why can we approximate this na ND yon for both of these cases? Because 17 and 13 is more than, is much greater than 10 because there's a difference of 3, no? At least 10 to the 17 and 10 to the 13 is much, much greater than 10 to the 10, no? Which is the intrinsic semiconductor concentration, right? Intrinsic carrier concentration for silicon. Anyway, no? Since we know this fact, let me just save that, no? So this is a fact that we know, no? And also a fact that if we leave the semiconductor in equilibrium, no, EF should be constant versus position, right? So these are our two facts. Then this means na, so what this means is that we can always draw EF. No? Apologies for the not straight lines because not very used to doing this anymore. Anyway, if we leave EF constant, no, then from this equation, what would we expect to vary? You would expect that EI is the one moving with respect to EF, no, with respect to X, because EF is always constant with respect to X, no? So EF of X is constant, meaning that EI is the one that's going to be changing, no? So relative to EI, in the areas of lower donor concentration, no? So in the areas of lower donor concentration, EF should be closer to EI, no? And then for areas with higher donor concentration, EF would be farther from EI. So I hope that one makes sense. By the way, no, as always, feel free to unmute and speak your questions or chat your questions if you do have any questions. No. Anyway, EI, no, is now farther away from EF here because the donor concentration is less here, right? Is more here rather. So then, if we were to draw the conduction band edge, no, all I'm gonna do is copy this. Of course, oh, oops, because I'm cheating. I don't want to draw that too many times. Yeah. So this is the conduction band edge, right? And we know that electrons really like being near EF, right? So mas maraming electrons dito, which kind of makes sense, right? Because there's more donors in that part. So ano yung conclusion natin from these observations, no? So this your energy E. Anong conclusion natin? The presence, no? The presence of actually kulang pa tong figure natin. May nakalimutan tayong very important part of the figure. May nakalimutan tayong very important part of the figure, which is EV, no? The other side. Anyway, yes, it shifts up or down. No? It shifts up or down kapag binago mo yung doping concentration. Kaso, apparently, no, from Fermi-Dirac statistics, the physics that the memes in our discussion page in Discord talks about, no, is that actually it's the Fermi level that's constant, and the thing that actually shifts up or down is the energy band diagram. So that's what we're saying now, no? Because it was easier to draw the EF shifting before, right? So dati kasi even yung doping concentrations natin, right? So we say na nag-shift up yung EF or nag-shift down. Depende. Kapag N-type, EFN yon, no? Or nasa taas siya. Kapag P-type, nandito si EF, right? Kasi mas maraming holes dito sa baba, no? Kaso, in actuality, we held EF constant and what we were moving around was this. Bakit hindi ko ma-select? Why does shift not work anymore? Tagal ko muna to. Yan. So, what actually happens is, no? Ito yung gumagalaw. kapag nagdo-dope tayo because EF is supposed to remain constant, no? Relative to some energy level. In actually, kapag naglagay ka ng voltage, saka magbabago si EF, no? Kaso in equilibrium, EF is always constant. And the thing that doping changes, no, is the position of EI with respect to EF, not EF with respect to EI, no? Kasi that's why yung equation natin is EF minus EI, not just EF. Kasi hindi nagbabago si EF, si EI yung nagbabago with respect to doping concentration. Let me see that here, no? So this is an N-type semiconductor, no? So an evenly doped N-type Si has band bending, is what we call it, no? So next, no? Let's talk about the energy, no, of a single electron. So this is the energy band diagram, right? EBD, no? Energy goes up this way. Meron tayong EI dito, no? So EC, EV, it's EI. Now, for an electron to be here, no? For an electron to be in this spot, it must break free from a valence bond, no? So actually, there's this concept called binding energy. It's okay. So back to one of the memes again. It's Captain America holding it in. So let's call the binding energy EBI. Actually, no. Wala pa tayong EB, no? So EB na lang, no? So if this is the binding energy that keeps the electron in a bond, no? Then if we give an electron exactly EB, then it just barely pops out, no? It's not going to move anywhere kasi we didn't give it excess energy, right? But if we give some more energy on top of the necessary energy that we needed to break it free from its bonds, then we're going to give it some extra kinetic energy, right? So intuitively, actually, this binding energy is actually 1.12 electron volts for a lattice, which is the same as our band gap energy, no? But actually, the binding energy depends, no, how deep the electron was in the valence band before we do it. But let's say for example na ito yung electron na pinag-uusapan natin, no? And we wanted to promote it up. If we gave it a little more energy, it would actually end up a little higher in the conduction band when it gets promoted, no? So, a way to interpret an electron's position in the energy band diagram is this is potential energy, no? Because kapag kapopromote pa lang ng electron from the bonds, hindi siya gumagalaw if you just barely get it out of the bond. What's left over, no? So what's left over after you break the binding energy is kinetic energy, no? So this is kinetic energy, the difference between the electron and the conduction band edge, and potential energy itong natitira dito sa baba, no? Now, something that's useful from this, no, is that is the observation, no, na electrons, no, when they move around, right, we have scattering, which means that an electron with high kinetic energy, after some time, it loses that kinetic energy, no? No matter what, because it keeps scattering around the lattice. If it has kinetic energy, it's moving somewhere, maybe randomly, but it's moving. So it gets scattered onto lattice, no? Which means that high energy electrons, very high in the conduction band, tend to fall down, no? Likewise, we don't have enough time for me to explain this, but the same thing happens for electrons, because they scatter as well, no? So the holes rather, no, the holes scatter upon the lattice as well. So this is kinetic energy for holes, no? You can think of it like as pressure in the water. So there's an air bubble very far down the water. So the buoyancy bringing the air bubble up is actually much greater, no? So what we can conclude from this kinetic energy, potential energy thing, no, essentially, is electrons sink, holes rise in the energy band diagram, no? And this is going to be important. The fact that electrons sink and holes rise, no? This intuition, knowing this by heart, no? Knowing that these things do these, the carriers do these things in the energy band diagram will allow you to understand why BJTs work the way they do and why diodes work the way they do, no? So let's go back to the uneven doping. Right. So here, no, with respect to X, hindi even yung doping natin. So what happens, let me just put this away. Bakit hindi na magana yung shift? Drag away part of the EI there. Yeah. So, for this uneven doping, kapag naglagay ako ng electron dito, what do you guys think will happen to the electron? Like, sige, lagay ko siya dito, no? In physics, no, if this was a rock, you would expect it to roll down, right? And ang conclusion natin kanina is electrons tend to sink, holes tend to rise, no? So actually, this bending ends up dragging electrons on it to one side, no? And likewise, holes, if they were here, will tend to rise because they're air bubbles, essentially, no? So this is what happens here. There is some mysterious force dragging these things one way or the other, no? Dragging the carriers across a bend in the band, no? So these slopes actually influence the motion of carriers. And you know what this motion is already because this is drift, no? So, in fact, this is drift, no? And you might say, okay, Sir Lo, paano naging drift yan? Eh, kailangan natin ng electric field para sa drift. Now, I'm gonna tell you that this bending in the bands is actually technically caused by an electric field, no? An electric field existing in an unevenly doped semiconductor, no? Remember, this is an unevenly doped semiconductor, N-type rather, N-type, by the way. If it's unevenly doped, it's going to have an electric field, a built-in electric field, no? So let's derive that. So I'm just gonna take one of these. Please let me just take one of these, Mr. OneNote. I don't know why you're not cooperating anymore. Right. So I'm just gonna take one of them. Say, for example, the conduction band edge, no? Now, if I told you that the voltage is the potential energy of electricity, you would say yes, no? There's no room for argument. That is what it is introduced as. No, voltage is the potential energy for electrostatic, no? So it's the electrostatic potential energy, no? So voltage, PE for charges, essentially, right? Or more precisely, no? It's actually negative. It's a negative potential energy, no? Because, bakit alam natin to? Because an area of higher voltage, papunta sa kanya yung electrons, no? Or rather, if it's high potential, positive charges go away from it, right? That's why it's negative QV, no? So, anyway, potential energy is negative QV. Doing some math, no? So, PE over Q, no? Eh, ano ba ang conclusion natin kanina? Diba ang conclusion natin is the conduction band edge is the potential energy of an electron, right? So this means that V is whatever the shape of E is with respect, divided by the electron charge Q, no? Tapos sabihin nyo, okay, naku po sir, may constant na naman. Kailangan ko bang tandaan yan? Yes, no? It's 1.602 times 10 to the minus 19. But, itong Q na to, it doesn't actually matter here. Bakit? Kasi ang units natin ng EC, right? EC of X is in units of electron volts. So if you divide that by Q, you get units of volts. Wala kang binago. Kasi Q is E, no? So it's just units. Yung presence ni Q dyan. But essentially, what this means is that, okay, sige, mali. What this means is that we can just flip this thing. Okay, flip it. Mali. It's vertical flip. Yeah, no? If we flip this thing, we get the voltage. The graph of the voltage with respect to X, no? So there exists a built-in voltage in an unevenly doped semiconductor because of this, no? And if there's a voltage, there's an electric field. Kasi alam natin, di ba, volts per centimeter ang electric field, which already gives you an intuition of kung ano ang electric field, no? The electric field is the vector field related to the scalar voltage field, no? So you must remember this from Physics 72. Actually, please do let me know kung hindi ito na-cover sa Physics 72, but I'm pretty sure you guys have, like, I think yung current triple E curriculum has 2 electromagnetics courses and 1 Physics 72. So I find it impossible na hindi pa to fact. So, um, like, can someone thumbs up kung alam nyo to or not? This is just the definition of electric field, no? Okay, sige. So, apparently it is known. So, kung ito yung definition ng electric field, for 1D, this would be d over dx of V, no? Negative. So, we would have this thing, no? So, E. And so then, if we take the derivative of this thing, I will cheat and say na ang derivative nito is ganon, no? Because I constructed this such a way that this is proportional to x squared. So then this would be proportional to x, no? So ganyan yung electric field natin. So then, we're back, no? We find that, okay, I'm gonna color this. Okay, never mind, I'm not gonna color that. So, we found, no, from this analysis that an electric field exists, no? An electric field exists. Sorry about that. Wait lang. Okay. So, tinetesting ko lang kayo is what I would say here, no? Anong mali? Anong mali dito? It's supposed to be flipped. Bakit? Kasi negative d over dx of v siya, no? Ay, hindi pala, no? Okay, tama pala siya. Testing you guys twice, no? So we're gonna do here is we're going to rotate it vertically again, no? So here, d over dx of v would be negative, no? Pababa kasi siya. So then we flip the sign, pataas na siya, no? So tama pala to. Okay? So now this is the direction of positive electric field, meaning that electrons go to the left because that's the direction of negative x, no? And holes go to the direction of positive x because it goes along with the direction of positive electric field, right? So, that's just nice. So it goes along with the intuition that these things roll over the slopes, no? And holes roll up slopes kasi they're air bubbles, right? And all of this is because uneven doping creates an electric built-in voltage, no? Which is the same shape as the as the energy band, but it's just flipped, no? Which causes an electric field because of this, no? Because it's the because E is equal to the gradient of V, and that causes the carriers to actually do the intuitive thing that we know they do, no? So, does anyone have any questions with that one? Yeah, I'm actually quite concerned. Am I still in the Discord call? Kasi, Discord call? The Zoom call? Kasi, nawawala yung, ito. Okay, drag it up there. Alright, yung meeting controls ko. Okay, so if no one has any questions about that, I will be moving on to the next part. Mahiwagang PDF, let me know what is the next part. Sige. So, why does an electric field cause these carriers to move, no? So ito pala, no. So I'm going back to this one, no? So copy paste that down here. Make sure it's clean, no? So to me it might have been an assumption na nangyayari to, no? An electric field causes carriers to move, no? That's an intuition, but let's quantify it, no? So J drift, this is, by the way, an equation that we've seen before, no? J drift is QN, not that one. QN mu N, no, mobility, times the electric field plus QP mu P E, no? Electric field as well. And both of them are positive. Bakit? Kasi nag-cancel out yung negative Q at yung negative direction ng velocity ng electron with respect to a direction of an electric field, no? So both of them are positive in this equation. So according to this law, these things will drift with respect to a positive electric field, no? Right. Now, what if I told you that in this unevenly doped semiconductor, no? There's also diffusion happening. And an intuitive way, no? J drift sa total current density. Hindi, no? Ano ang total current density? J total. And what is J total? There's two types of carrier action na diniscuss natin. Actually, tatlo, no? Kasi yung isa is basically the generation and the combination of carriers, no? Which doesn't actually affect current. This is J drift plus J diff, no? And that's what I'm like leading to, no? By the way, naka-disable ba ang everyone? No? Naka-everyone naman eh. Like, don't be shy to each other. Like, stop DMing me para nakikita ng ibang tao. So, ang question na pala is sir, same din po ba yung J drift's total current density? And it's not, no? Kasi there's a missing portion. It's the diffusion current, no? Which we also discussed last time, right? Now, di ba sabi ko, this semiconductor is in equilibrium. No? This unevenly doped semiconductor is in equilibrium. Kaso, kung nagkakos ng drift to, hindi ba malalaglag yung electron mo dito sa dulo na to? Tapos may ma-measure ka ng current gamit yung ammeter? Yes, kung drift lang, no? But, note that the fact na nangyayari to, no? So, okay, sorry, pataas. That's supposed to be flat, no? So, this is, ano, di ba? EC saka EF, no? Or rather, saan ko ba ilalagay si EI dito? I'll just delete EC here and replace it with EI, no? So, si EI to. So, kung si EI to, no? We know that N, no? So, balik rin natin yung equation for EF minus EI kanina. N is proportional to Ni scaled with E to the 0.026 electron volts. EF minus EI, no? So, there's an exponentially larger amount of N on this side as opposed to what is there on this other side, right? Does this make sense? No? So, E to the this thing is equal to that thing, no? E to the this thing is equal to that thing, no? So this thing, yung differences in energy ni EF at saka ni EI, you put that in an exponential, you get the actual carrier concentration, no? Electron concentration rather, for this one, per cm cube, no? And likewise, hindi lang sa ganyan nangyayari yun. Kasi we also have holes, right? Which so this is holes, no? This is P per cm cube, no? But there's much less holes. Bakit? Kasi NP equals Ni squared, di ba? Which means P is equal to Ni squared over N. So P is equal to Ni squared over N, right? Which means that if N rises, P goes down. No? Kaya ganun yung tsura niya. No? So, what's so special about this, no? Bakit ko pinoint out na nagbago yung carrier concentration with respect to X in this in an unevenly doped semiconductor? Bakit? What's so special about a what's so special about the what happens, no, rather, when the concentration of carriers varies over position? So just like smoke from an exhaust, what happens is that there's diffusion, no? Because J diff is equal to Q D. Let's just treat N for now. Bakit? We can assume away the holes because there's so much less holes than electrons. No? So whatever the electrons do, that's what that's what shows up in the macroscope essentially. No? So Q dN dN over dx. No? So this is J diff, right? This is the diffusion current. It's proportional to the direction of the positive slope of the carrier concentration, no? And likewise, no, dun sa gradient natin kanina, actually, this is QDN, gradient of N in general, no? If it's not one-dimensional yung example natin. Anyway, this means na this means that this current, no, this means that the electrons diffuse that way, No? Right. So the electrons diffuse to the right, no? And this is special. The electrons diffuse to the right. Eh, ang conclusion natin kanina is the electrons drift to the left because of drift, no? So, because of diffusion, they actually go back, no? And likewise, holes also drift that way, also diffuse that way because of this, no? So holes go that way, right? Which means na ganun yun, no? Now, just because we know that the direction of diffusion over the junction, oops, spoiler, it's not a junction, no? This is still just an unevenly doped semiconductor. Just because we know the opposite yung direction diffusion sa ni drift current doesn't mean na nagka-cancel out sila, no? And to prove na nagka-cancel out sila, I did the math, di ba? So let's open the slides now. I did the math and it turns out to be like this, no? Did the math meaning I used Desmos and plotted everything, right? So from this we get basta yan, no? So from this unevenly doped semiconductor we get the voltage, no? We get the voltage which is the same shape as the conduction band but just negative, no? And then we take the derivative to get the electric field, no? The negative derivative. Now, since we have the electric field, no, we can get the drift because the drift is n, no, this thing times this thing equals that thing, no? So we get the drift current, which is like a kind of a wobbly triangle now. Tapos, ang diffusion is we take the derivative of this thing, no? And what's interesting about this derivative is, sige, I'm gonna take the derivative on the spot. This is going to be 0.026. Actually, no. Um, um, uh, right. So we get this thing again, but the derivative of this thing is actually just electric field, right? Kasi the derivative of this thing, which is the same shape as the voltage, is essentially the electric field nga, no? Just flipped signs. So this actually becomes E, no? Which is the same thing we calculated there, right? Just opposite sign, no? So we get that the diffusion current is actually exactly the negative of the drift current that we calculated. So nag-cancel silang dalawa. And which makes sense, no? Because if you have an unevenly doped semiconductor and you leave it on the table, it's not like the electrons start falling out of one end, no? No, they remain there. That's because the drift and diffusion actually cancel out in equilibrium for any semiconductor, no? So anyone have any questions about that one? All right. So if no one has any questions about that one, let me just move on. No, move on by giving you guys something to do. No, so this was made for face to face. Now I don't know how to make you guys do this. Mm, sige, ilalagay ko to dun sa Google Forms, no? Di ba? Sige, what I'm gonna do is I'm going to draw something on this slide, no? So this is section A, section B, no? So, tapos, ang question na ilalagay ko dun sa Google Form is section, what direction? Right. I added it dun sa Google Form. As always, though, meron namang merong feedback area, like merong feedback questions to Google Form na to. Which means that ideally you only submit it at the end of the class. So just um take note of this of your answers for this part and lagay nyo na sa Google Form once you fill up the Google Form for the attendance. So, let me just put it here as well. I put it in the attendance channel as well. Right. So let's take around a 10-minute break and then I'll continue with the PN junctions. No? Of course, I'll leave this slide open so that you guys can try to do the activity. Kamusta pala traffic today, guys? Or I guess you guys never went to UP today kasi may notice na like wag na online class dapat today. Puro online class lang today. Okay. That's nice then, I guess. So, probably no one experienced the traffic. I didn't either because I went home to Laguna yesterday. All right. Sige. So that's 10 minutes. Finish or not finish. Hindi niyo pa naman kailangan mag-submit. Um, I'll just go ahead with the lecture, no? Sige. So, now that we have for unevenly doped semiconductors, paano naman mangyayari kapag nag-join tayo ng dalawang oppositely doped semiconductor, no? Now this one is nice, no? Because it gives birth, no? Kasi di ba sinabi ko kanina, this is your PN junction, right? And it's a diode, no? So bakit siya nagiging diode? We'll find out soon. Right. So kapag nag-connect tayo ng isang P-type na semiconductor saka N-type na semiconductor, they would still be in equilibrium. It's not like electrons, no? Kasi intuitively, no? Electrons will infinitely flow from there. Holes will infinitely flow in that direction, right? That's the intuition, no? So, like, and then you're gonna say, uh, all right. So then actually no, there's a very high amount of total current going that way, no? No matter what. Well, the fact that they're in equilibrium means that the drift is going to do something to stop this, no? So let's see what it does. So when we connect these two perfectly, no, by some sort of space welding, makikita nitong electrons na to, oh, free real estate that way. Holes see that it's also free real estate that way. So tama, pupunta yung electrons dun sa, the electrons will go towards the right, holes will go towards the left, no? So here, ginawa ko is, no, because the electrons went to the left and the holes went to the right, they met in the middle, no? Rather, the electrons went to the right and holes went to the left, no? They met in the middle. And we know what electrons and holes do when they meet, no? It's the kiss emoji, which means that they disappear, no? They recombine when they meet. So, ano nangyari? Walang naging carrier sa gitna, no? This is called depletion, no? So actually, the interface, no, or not just the interface, no, a little into the joint between a p-type and an n-type semiconductor, if you join them together, this becomes a depletion region. Because carriers near the junction actually end up recombining with each other, no? So near the junction, there are no carriers left, and we call it a depletion region, no? All right, so that's enough of the slides. I'm gonna take over now. Actually, let me screenshot this thing because it's a really nice figure. Thanks, Lawrence of the past. Kaso, no? Oops. Okay. Um, Observe what happened, no? So there's a reason why I put plus here and minus. So the dopants for the N-type side, no? So this is N-type. This is P-type. Yung dopants natin for the N-type side are phosphorus atoms that lost an electron. Meaning, ang matitira sa kanya, kapag wala na yung electron, is a net positive charge. No? Kasi lahat ng phosphorus atoms natin dyan ngayon ay positively charged na. Kasi nawala na lahat ng electrons nila that are supposed to be canceling out that positive charge. No? Now, for the p-type side naman, the donors lost, the acceptors rather, lost the whole, no? Or rather, they gained an electron when that shouldn't be there. So, what happened is that we have a net negative charge for each dopant site dun sa p-type na side, no? So, if this was a graph, no? Which it will now be because I said so, no? And this is charge density, right? So, charge density rho, right? By the way, sino nakakatanda kung ano dapat ibig sabihin ng rho from last session? Yes, it stands for resistivity. So, be careful, no? Because it stands for two things, actually. It also stands for charge density, no? So, charge density is basically the density of charge, no? So, how densely, no? So, it's coulombs per centimeter cube, which should tell you a thing, I guess, an intuition of what it's supposed to mean. It's the amount of charge per centimeter cube, no? Per spatial area. Kasi ano, parang when you say this balloon, no? So I rubbed I rubbed leather on top of this balloon and it got 1 coulomb ping, of charge, no? We're talking about the total charge, right? So this charge is actually split over the volume of the balloon, which means that we have a charge density. And if we integrate the charge density, we get the whole charge. No, we get the whole charge Q. So Q is equal to integral of P, essentially, no? Over the volume. Yeah. Anyway, no? So since the N-type side has dopants, no, that's donors that are positively charged, no, those are left behind, then we have positive charge density doon. Tapos, dito naman sa P-type side, we have negative charge density. Kasi, acceptors ang natira doon. And they have one more electron than they're supposed to. No? So that makes sense, right? Now, one thing is, no? Let's add one name to our list of names, no, that helped us. Poisson. Poisson. It's Poisson's equation, no? I know that first one was wrong. That really did sound wrong. Poisson's equation says that the charge density, no, rather, mali pala ano yung simula ko. The divergence of the electric field is equal to the charge density over the dielectric constant of that material times the permittivity of, sorry, wait lang. I may be using the term wrong. I don't remember if this is permeability or permittivity. This is the permittivity of free space. Yes. So this is permittivity. Right? So this is Poisson's equation. No? Poisson's equation. And it relates the charge density raw, no, not the resistivity. It relates the charge density raw with the electric field. No? Essentially, the divergence is like derivative, but for vector fields. No? And since it is like a derivative for vector fields, then dE, no, dx is equal to rho over ks epsilon naught. No? Or in other words, no, the epsilon, the electric field is actually the integral of 1 over ks epsilon naught rho. No? Rho dx. No? So integral of rho dx from negative infinity to actually no. From 0 to x dx plus c essentially is what's going to happen here. So sige nga, let's make it this indefinite na. Don't care. Yeah. Yeah, so that's all I really wanted to say. Poisson's equation. Now we're gonna use it. No? We're gonna use it for noble causes because we want to derive this thing called the section, no, the topic that we're now talking about, which is the PN junction electrostatics. All right. So the thing about the PN junction is, ayun nga, no? This charge can be approximated, no? If we assume that we have a uniform doping for each side of the PN junction, no? Then, and hindi compensated, no? Meaning that only ND and only NA is present here, no? So hindi siya compensated. You don't bombard both with differing types of dopants. This means that QNA, ito, no? So this is QNA and this is QND, no? So I hope that that one kind of makes a little bit of sense here. Kasi bakit? Why would it make sense, no? Kasi NA is per cm cube, no? So that's per cm cube. So we get coulombs per cm cube, meaning this is charge density kapag minultiply natin sila, no? So it is actually exactly that, no? Right. Now, back to Poisson's equation, no? Poisson's equation is just, integral of T is proportional to E, no? That's essentially what it said, no? With some proportionality constant, it's 1 over ks epsilon naught. So, kapag in-integrate natin to, what we get is the electric field, no? And we get the electric field is linear. Bakit? Kasi the integral of a constant, no? Of a box, essentially. The integral of a box is a line, no? So we get that the electric field goes up and down here. No? So I hope that makes sense naman. Right? In a PN junction, apparently, when they meet, no? So again, they met, nag-deplete, may naiwang dopants, the charged, which left behind the charge density like this, no? Nag-create yun ng electric field. And what do we know about electric fields? They cause band bending. Oh, and I cheated, no? Because I used the linear thing already, so we don't have to rederive. Now we know kung ano itsura nung energy band diagram for the PN junction because we've already done it here, no? So I'm going to copy paste this, place it down there, no? But there is one difference kung ano yung energy band diagram ng isang PN junction. The difference is this thing crosses the EI line because the two sides of the PN junction are oppositely doped. No? So please let me erase. Yeah. So this means that EF crosses from the N-type side, no? This N-type to the P-type side. And this is your PN junction, no? By the way, ano yung shape nito? It would be x squared, no? Quadratic yung itsura niyan. Bakit? Kasi linear yung E. Tapos in-integrate natin yun, nakuha natin quadratic, and we got the energy band diagram because that is the voltage, no? So, ano, does that make sense? Anyone have any questions? Just trying to make sure na yun na yung last. Okay, never mind. That's not the last. We have one last thing, no? And that last thing is actually very intuitive. And I actually like it very much. So, not very sad about having to extend, no? So, ito yung energy band diagram natin for a p-in junction, no? Actually, sige, screw this drawing. I'm going to screenshot the p-in junction that I already have drawn really well with the SVG, not my hands. Okay. We find, no? Oh no, it's on the wrong direction. Anyway, same pa din naman. We find, no, na, di ba energy is the same as voltage but flipped? So, between the P side, no? So, ito na yung P-type side. And this is now the N-type side. So, between the P-type and N-type sides of a PN junction, there is a voltage difference. Bakit? Kasi may difference in potential energy, right? This is potential energy. That's PE. This is PE. No, so PE1 is greater than PE2, meaning there is a potential difference, right? So there is a measurable built-in voltage. And you are lying if you tell me that you've never seen this built-in voltage before. Typical values of this thing. Can someone tell me typical values of the built-in voltage? 0.7. Right. So we've seen macro scale consequences of our semiconductor things. No? Just because the electrons leave their dopants and the dopants are left behind as charged, charge density, no? They cause the divergence of E comes from the charge density, no? Nagkaroon ng linear na electric field. So nagkaroon ng quadratic na band diagram. Tapos nagkaroon ng built-in voltage. And this built-in voltage is what we see on macro scale na lumalabas sa diode across it. No? Now, equation. It's very easy. No? You understand kung bakit very easy. Kasi, um, let me rethink this kung ano yung equation. Tama yung equation na ilalabas ko, by the way. So don't doubt that one kasi I'm rethinking kung tama yung equation. Hmm, Tama. Anyway, sige. So, ito ang equation ko, no? So, the built-in voltage, sabi ni Pierret, by the way. So, sinabihan ako ni Sir Fred. Apparently, I'm wrong about it. It's not Pierre. It's Pierret. For a guy who has read this book for a very long time. Apparently, I'm wrong. Anyway, the built-in voltage is KT over Q, which is just 0.026 volts, no? Times ln of NA times ND over NI. And NI squared. So, this one is nagbabag yung one note or something. Right. NA is the NA of the P-type side. ND is the ND of the N-type side. No? Now, why do I say that this thing is actually quite beautiful? If I rearrange this, whoa, right? And if I rearrange this equation, I'm gonna get VDI equals KT over Q. No, this one is actually not important anymore. But ln NA over NI plus KT over Q ln ND over NI. This is that equation rearranged. And let me just do this again. Right. So, the reason why I said this is intuitive is kasi, essentially, inad mo ito plus ito to get this, no? And the thing that I had to rethink earlier is kung geometrically this makes sense, and it does, no? So essentially, if you add this thing, right, which is EF minus EI, no? For the N-type side, yun. EF minus EI minus EF for the P-type side, yun, no? So this equation, by law of logarithms, pluses becomes times, no? Actually makes sense. Just from a geometrical perspective ng energy band diagram, no? So with that ends our lecture for today. Let me just pull up the lecture summary slide. All right. So if anyone has any questions, feel free to ask them. I will stay until 4 o'clock. To those who have other classes, feel free to leave and start preparing for your other class. And see you guys on Friday, which is also an online class. No? So Wednesday, next week na lang tayo magsimula ng offline class. Ng F2F para dati.
Thank you po, sir.
Right.
Thank you, sir.
Thank you.
Sir, pwede pong mag-ask.
Yep. Yes.
Sir, doon pa sa part ng when we were discussing about drift and diffusion po.
All right.
Ano ba yun? Sir, so, yung ginawa po kasi,